Hi everybody, myself Dr. Balamurugan, working as an associate professor in the Department of Triple Rangasamy College of Technology. Myself going to discuss about the resonant converters, that is nothing but HZVS and HZVS DC to DC converters. So let's we enter into the topic. So first of all, we have to differentiate between the linear power supplies and why we are going for high frequency pulse width modulation regulators. So basically, linear power supplies has the advantages like low cost, fast dynamic response. So we are preferring linear power supplies. But the major disadvantages is efficiency is low when compared to the other switching converters, and also we can get only one output at a time. So for that, we are using the high frequency PWM switching regulators. So what are the advantages of that high frequency PWM switching regulators are? Multi output applications are available, size and cost is much lower, and also even though it has more advantages, it has also some of the disadvantages like high electromagnetic interference, and also the circuit complexity is more when compared to that of the linear power supplies. So for these things, we are preferring the resonant converters. So what are the major advantages of resonant converters in DC to DC converters means? So first of all, we can provide natural commutations at zero current and zero voltage. So it will reduce the switching losses. So low power switching dissipation, and also the switching stress in that switches will also get reduced. This results in a low increased power efficiency and increased switching frequency also. And the operating frequencies of these converters are high compared to the other converters. And important thing is there will be no EMI problems. So next we can compare these resonant converters with conventional PWM. As I have said, EMI caused by the PWM will be low compared to that of the normal PWM or normal converters. And when we compare these PWM converters with resonant converters means EMI will be fully reduced. And also important thing is power dissipation is also reduced due to the less switching losses in the resonant converters compared to that of the conventional PWM converters. And another thing, the designing of this PWM converter is somewhat complexity compared to the resonant converters, because we can insert only the resonant network in order to have a resonant converters. The next third thing is the advantages will be harmonic current content will be reduced, voltage and current waveforms will be improved. So PWM converters will have advantages over normal linear power supplies, but over the resonant converters, when we compare this PWM converters, the resonant converters will have a very good advantages of having a clear voltage and current waveforms with reduced noises. What is short switching? So why we are in need of short switching? So short switching is nothing but switching the devices at zero voltage and zero current. And next thing is, what is the advantages of short switching? Suppose if you are turning on and turning off the devices with zero voltage and zero current means we can have a reduced switching losses, we can have a reduced switching stress and possibly low AMI, and main thing is we can have a thermal management. So next thing is we can also have a high frequency operations and switch rating, component usage, this will also get reduced. So for these major applications we are going for surf switching. So what are the problems in hot switching? Main thing is switching losses, EMI and thermal management. So for these reasons we are in need of a HZVS and HZCS converters. So HZVS is nothing but zero voltage switching, HZCS is nothing but zero current switching. So these are the classification of soft switching resonant converters: quasi resonant, full resonant, quasi square wave converters, then zero transition topologies. Every topologies will be working under zero voltage and zero current switching. So this will reduce the switching losses. So basically we are going to see only the two things, ZPS and ZCS, zero voltage switching and zero current switching. Main advantages are lower switching losses, it reduces the EMI and it allows a high frequency operation of the converters. And you can see the switches which is shown here, zero turn on, zero turn off. So zero turn on means we have to the switch voltage brought to zero before the gate voltage is applied. So this will have a zero loss transition during the turn on. Same way, during the turn off, low loss transition, because we have to make the zero voltage across this device to zero. So this will help the zero loss transition. So preferred scheme for higher frequency application using MOSFET, because in zero voltage switching we can prefer MOSFET for all the applications. So this is zero current. Here the switch current is brought to zero by using this network, and we can make zero loss transition. During turn on, low loss transition will be there due to the presence of series inductor with the switch. So it can be best suited with IGBT due to its tail current at turn off, because we can have zero current switching with the help of IGBT for many applications. And advantages of zero voltage and zero current. So power switch is turned on and turned off at zero voltage and zero current. In ZCS topologies, rectifying diode has ZVS switching. In ZVS topologies, rectifying diode has a zero current switching. So both the switching will be using the alternate switching sequences for a device which is connected in parallel to the main device. So in isolation topologies, both we are using both ZVS and ZCS. Here we are using the transformer leakage reactances and diode junction capacitors and output parasitic capacitor for power switch. So in ZCS, the power switch turns off at zero current, but at turn on, the converter will suffers from turn on losses. But in ZVS, we can turn on by using the ZVS topologies. Or the zero current switching topologies available with resonance switching. So you can see the L-type switch, which is nothing but A. We can see the L-type switching arrangement. We can see the half-wave implementation, and we can have a full-wave implementation. So L-type, M-type, and half-wave and full-wave with unidirectional, bidirectional devices. So LC tanks can also be preferred for resonant tank in ZCS. And this is M-type switch, and you can see the resonant switch which having the half-wave implementation and full-wave implementation. So the last topic here is just we are classifying the soft switching schemes which is available for controlling the soft switched devices. Load resonant converters are available. Converters with resonant switches, quasi-resonant, multi-resonance are available. Resonant transition converters are available for different applications for having a zero voltage and zero current switching schemes in order to have a low EMI and also low switching stress with better thermal management techniques. So thank you for giving this opportunity. Thank you.